Okay, so this is the Projectile Motion lab, and what we want to do in this particular lab is ultimately we want to look at the relationship between the range of a projectile. So what that means is from the point of projection, so when the ball leaves the gun, to a point on the path that's at the same elevation as the point of projection. So that horizontal displacement that's at the same elevation is called the range. So ultimately we want to see or determine how the range is affected by the angle of the gun. So we're going to vary the angle of the gun, find the range, and look at that relationship. Okay? So the first thing that we need to do in terms of collecting data is we need to figure out the speed of the ball, or the velocity of the ball, as it leaves the gun. So we need the launch velocity of that ball. So to do that, I have a photo gate that's connected to the end of the gun. And I know the diameter of the ball, so the ball happens to be 1.90 centimeters, so I have its diameter. And using the CBO timer here, I can compute the time it takes the ball to pass through the photo gate. And the timer is set, or the timer is set up, the photo gate set up, so it's right at the end. It's right when the ball leaves the gun. So if I know the time that it takes the ball to pass through that photo gate, if I take the diameter of the ball, that's sort of like my displacement, like my delta x, divided by the time it takes to pass through, that's going to give me a very good estimate of the velocity at that location, which is right when the ball leaves the gun. Okay? So let's do that first. I'm always going to use the first setting on the gun here. So put the ball in, I'll reset this, and I'll fire it, and let's record that time that it takes to pass through. I'm doing this, by the way, at 3 angles. So this is at 15 degrees. I will also compute the time at 45 degrees and then at 75 degrees. Okay, so this is at 15 degrees. They should be pretty similar. Okay, I'm getting 0.0052 seconds. And I will give you guys all these values so that you have, so you can use them to do the lab report. But I just want to walk you through how I'm collecting some of this data. Okay, so now I'm going to 45 degrees. Same thing, I'll reset the timer, fire it, 0.0054, so that's fairly close. And then one more angle, I'll also do this at 75 degrees. So reset, fired, 0.0055. Seconds. Okay. So now what I can do is I can calculate the velocity for each of those 3 angles. And again, they're pretty close, right, because the times were very similar. And then I'm going to average those velocities to get the launch velocity of the ball. Actually, you guys will do that. I will give you that data. You can calculate the velocity for each angle and then average all 3 to get the final average velocity, which we're going to call the launch velocity of the ball. Okay, the next thing that I want to do is I want to get the range values now. So let me just show you for a few examples how this is going to work. First of all, we can remove this. I don't need the photo gate anymore. Just needed it for the initial part where I wanted to find the velocity of the ball, so I'll move this out of the way. I'll do it at 45 degrees, just as an example. But ultimately, I'm going to calculate the range for several different angles. Okay? So first of all, at 0 degrees, we know that when the ball launches, it's immediately going to fall. Right? So when it leaves the gun, it immediately starts to fall due to gravity. So therefore, since it never gets back to the same elevation it was launched at, the range is 0. And that's already built into your table. So at 0 degrees, the range is 0. And then we're going to, or I'm going to collect the data for 15 degrees. I'll do 3 trials at 15 degrees of that range, 3 trials at 25 degrees, 35, 45, and so on up to 75 degrees. And then at 90 degrees, so when it's going straight up, the range is also 0, right? Because it launches, it goes straight up, comes back down, but that horizontal displacement is going to be 0. So at 0 degrees it's 0, and at 90 degrees it's 0. Now you might know that as you increase the angle, so as I go from 0, 15, 25, and so on, the range is going to get greater. It's going to increase up to a point. And theoretically, if we ignore air resistance, 45 degrees should give us the largest range. Okay, so I'll just show you a few data collections at 45 degrees. So first thing, we have to make sure that the landing platform is at the same height as the gun. So I've already measured this earlier, so the top of this table right here, the top of this platform, is at the bottom of the gun. And if you notice, I have a piece of carbon paper on top of a piece of white paper. And the reason for that is when the ball hits the carbon paper, it'll leave a mark on the white paper. And then I can simply measure the distance from that mark. I can pull this back, measure the distance from that mark to the edge of the gun in centimeters, and that's going to be my range. Okay? So basically, I'm going to do 3 trials for each of those angles. So let me just show you a couple of these. And we might have to adjust it. I'm not sure exactly where this is going to land. So this is 45 degrees, right? First setting, launch it. Great, it hit perfectly. So it leaves a little mark here. And now I can measure from that mark to the edge of the gun. So in this case, it's around 110.1 centimeters. And that will be my range value for that particular trial. And again, I'm going to do 3 trials for each of those angles. Okay, and then I will give you guys all that data, so you'll have all that data. And in another video, I'll explain the entire lab a little more carefully. But this is the important information you need to know, at least how we're collecting the data.